Hello again and welcome to the night class. I'm your favorite math teacher, Coach Knight. Hope everyone's doing well out there today. Today we're going to talk about Lesson 6.3. Lesson 6.3 is Exponential Growth and Exponential Decay functions. So basically we have functions that will be growing exponentially or decaying exponentially, which means they're growing really fast or they're getting smaller really fast. So let's jump right into it. It tells you in example 1, this is exponential growth. So we're going to be growing here. We're talking about the population of Hillville. It says it grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? So if you remember the other day, we did exponential functions, and it looked something like y equals a times b to the x power. Okay, so this is basically the same type problem, except we have a growth rate this time. We're growing, and we're growing by 15%. So we're going to change this up just a little bit. Not much, okay? Just a little bit. And we're going to change this to where we include the growth rate. So this becomes, rather than y equals ab to the x power, y equals a times 1 plus r to the x power. And so the 1 plus r, 1 is just, if it was just 1, it wouldn't change at all. And r is what your growth rate is. So for this particular problem, we'll have y equals, a is still the initial value. It's how much you start with. So our initial population is 5,000. So 5,000 times 1 plus our growth rate is 15%. So we change that to a decimal, would be 0.15 to the x power. So we have y equals 5,000 times 1.15 to the x power. So if you just want to write it all at once, that would be how you write it. And they want us to know what's the estimated population in 5 years. So basically all you have to do is plug in 5 for x. So y equals 5,000 times 1.15 to the 5th power. If you put all of that in your calculator, you will see that you get, let's see here. Let me plug it in my calculator. Looks like 10,056.79 people. Now, it would be a really neat trick to have 0.79 of a person, so we'll just round that up to 10,057 people. And again, that's in about 5 years. So in about 5 years, we've more than doubled our population. Another example, same type question. It says the population of Valley Town is also 5,000 with an annual increase of 1,000. So this time it's increasing 1,000. Can the expected population of Valley Town be modeled with an exponential growth function? And the answer to this is no, because it's not. See, here with Hillville, it was growing by an annual rate of 15%. Valley Town is increasing by 1,000 every time. So that just means if it starts out with 5,000, by the second year, it'll increase by 1,000, so it'd be 6,000. By the second year, or first year, it'd be 6,000. By the second year, it'd be 7,000. By the 8th year, it'll be 9,000, and so on and so forth. So this is actually a linear model rather than an exponential growth model. So answer would be no, this is a linear model. And again, it's just a linear model because it's growing the same amount each year. It's growing up by 1,000 each year. Okay? It increases by a constant value, not by a constant rate. Interest. Interest is calculated in two ways. There is simple interest, and there is compound interest, okay? Simple interest is interest paid only on the principal. So, in other words, simple interest is interest only paid on the principal. So, if your interest rate is 10% and you plug in $1,000, you're going to get $100 off of your $1,000 because 10% of $1,000 is $100. Compound interest is interest that is paid both on the principal and on the interest that has already been paid. So basically, you get to take your interest and add it to the principal and then get interest off of both of them together, okay? So here is the compound interest formula. You need to make sure you know that. These are all the parts. If you notice, it's very, very similar to just regular old a b to the x. Now, there's some things have changed. A is now p, okay? A is your principal. That's the initial value, all right? B is all of this in the parentheses. So if you remember just a minute ago, we had B was equal to 1 plus R, and that's a growth rate. So most of the time, interest is growing. So 1 plus R, we've added a little bit because the ends are what take the compound place, okay? And then your T is like your X. So your T is how many years or how long would this be going on? How long will you have it in the bank? Or how long will you be borrowing from the bank? Just depends. So it's very, very similar. And this kind of shows you the graph, the difference in them. As you can see, simple interest is a linear equation, whereas compound interest has a little curve to it. It goes up. So compound interest always increases faster than simple interest, okay? So let's try one. Example 2 says Kimberly's family invested in a certificate of deposit for her when she was born. The interest is compounded quarterly. What is the value of the CD at the end of the 5 years? So what we're going to do is I'm just going to write the equation here, just so we make sure we know everything. R divided by N to the NT power. All right, so A is what we're looking for. We're looking for the amount principal. All right, so that's how much we deposited. So over here, it shows us $3,000 is our deposit amount. So that's P is 3,000 times 1 plus R is your rate. Our interest rate is 8%. So that will be 0.08 divided by N is the number of years we're compounding. So we're doing this over 5 years. Okay. Oh, I'm sorry. It's over 5 years, but it's being compounded quarterly. Okay, quarterly. So if we're compounding, N is the number of times you're compounding it. So quarterly would mean 4 times every year. Okay, so if you're doing it quarterly, you do 12 divided by 4, or excuse me, how many months would it ever be? So every 3 months is when we're doing this. That's what quarterly is. But quarterly is how many times it's being compounded per year. So it's being compounded 4 times per year. All right. And then times, N again is 4, and then T is 5. So 5 years, compounded 4 times. Put all that in your calculator at once, and you will get your final answer, which is $4,457.84. And again, that's just putting everything in your calculator. There's nothing hard about it. It's just making sure you plug in all the right numbers. Okay. So you can compound things monthly. If you compound it monthly, that means you'll compound it 12 times in a year. If you compound it weekly, you'll compound, that would be, N would be 52. If you compounded it daily, N would be 365 because there's 365 days a year. So it just really depends on how many times you're compounding and what are they compounding it by. So let's try part B here. It says, will the value of Kimberly's CD be greater after 15 years if it is compounded annually rather than quarterly? So this time, all right, we have to do it twice. So again, I'm just going to write my equation up here. I do this to help me memorize the equation. So 1 plus r over n to the n times t power. So for my first one, I'm going to try, let's see here, compounded annually rather than quarters. So annually just means once per year. So let me come over here. A will be my principal is still 3,000. 1 plus R is still 8%, so 0.08, divided by 1, because we're annually is 1, so to the 1 times 15 power. Put that in your calculator, and let's see, let's put that in. That will be $9,516 and 51 cents. All right. And we do all that again, except this time we're going to compound it quarterly. So quarterly would be the same problem. It's just rather than dividing it by 1, we're going to divide it by 4 and multiply it by 4. So 4 times 15 power. And we put that in our calculator, and we will see that we get $9,843.09. Okay? So as you can see, if it's compounded annually rather than quarterly, we're not going to make as much money, because think about it. Annually just means we're compounding it once per year. Quarterly means we're compounding it every 3 months, basically. So we would, every time it's compounded, we're making more money. So it would be more. Okay, quarterly, how do I say this? Let's see here. Quarterly would be greater than annually. Okay. Another problem, same type problem. Kimberly's family invested in a certificate of deposit for her when she was born. The interest is compounded quarterly once again. What is the difference after 15 years if the CD is compounded semi-annually rather than quarterly? So we have to find 2 answers, and then we want to find the difference, which means we have to subtract them. So let's do it quarterly first. So A equals, again, we've still got $3,000 times 1 plus our rate is still 0.08. We're compounding it. We're doing what? Semi-annually. So that would be twice. And then to the 2 times 15 power, 15 years. Okay. Put that in my calculator. Give me a second. That's going to be, let's see here, after 15 years. Messed up plugging it in. I'm sorry. Hold on. All right. That's 9,730 and 19 cents. And if we did it quarterly, that's going to be 3,000 times 1 plus 0.08 over 4 times 4 to the 15. So give me a second. Let's put that in our calculator. That will give us $9,843.09. So if we subtracted those, 9,843.09 minus 9,730.19, the difference between them will be, drum roll please, $112.90. always answer what the question asked. It said, what was the difference? What will be the difference? So that is it's $112.90 less. Part B, we're going to skip part B because it's the same thing, only now you're comparing it compounded monthly rather than quarterly. So actually, it won't take long. Let's try it. Let's see here. Monthly, we're going to plug in 12 for n because there's 12 months in a year. So let's see what that would come up with. So let me grab my calculator again, plug everything in. And that is $9,920.76. So if we subtracted 9,920.76 minus quarterly was 9,843.09, that will be $77.67. So $77.67 more if we compound it monthly rather than quarterly. All right. Example 3, we're starting to talk about exponential decay. So all of those problems we were gaining. Exponential decay is when you lose. It gets smaller over and over again. So same basic equation. However, this time we did have y equals a times 1 plus r. So now since it's decaying, we're going to have 1 minus r to the x power. So again, everything's basically the same. It says 1,000 views per day. A video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. How many days total will the video stop being a fan favorite? So basically we have to figure out when will it start being viewed less than 1,000 times a day. So here, let's see here. So we know I need 1,000 times is going to equal, A is how much it started out with, so 8,192 views, times 1 minus, my rate is 0.25, 25% to the x power. So 1,000 equals 8,192 times 0.75 to the x power. Now, that would be pretty hard, except we can use our calculator, and we can find, using our calculator, about where it would be 1,000. So just to let me show you, you go to your y equals on your calculator, you're going to type in your 8,000, well, I lost it. How much was it? How many was it? 8,192. 8,192 times 0.75 to the x power. And we graph that. And as you can see, we can't even see the graph. Thankfully, we don't always have to see it. We can also go to the table. So hit second in graph and go to the table. And I must have done something wrong. What have I done wrong? Let me see here. I put up here plus x. That is not correct. I need to delete that. Now it's to the x power. Now let me graph it. Do I still see it? I still don't see it, but I can still go to my graph. There we go. Go to your table, and you're looking for when is x 1,000. So it looks like at 7, it's 1,093.5, and then at 8, it's 820.125. So my answer to that one would be about 8 days. Okay, when it gets to about 8 days, you're going to be below 1,000, and you won't be a fan favorite anymore. So about 8 days. So X would be about 8 days before it's not a fan favorite. And again, that is an estimate, okay? That is not an exact number. It says try it. A video is labeled a fan favorite if it reaches 1,000 views per day. Amelia posts a video that gets 8,190 views on the first day. This time we are decreasing by 20% per day. So same problem, but this time we're going by 20%. So we're going to have y, which again, we want it to be 1,000. It says less than 1,000. So 1,000 is equal to, we start off with 8,192 times 1 minus 0.20 this time to the x power. So we're looking for, where does 1,000 equal 8,192 times 0.8 to the x power? So again, we go to our calculator, change that, instead of 0.75, we're going to go 0.8 and hit graph. And our problem is we still can't see it. That's okay. Go to my table, second graph, and it looks like about 10 days it will be less than 1,000. Okay, so there's 9 days, it's at 1,099. 10 days is at 879. So our final answer is about 10 days. Okay. Exponential models of decay. So same thing. The number of pica in a region is decreasing. Important. Decreasing. How does the decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? So the first thing we need to do is figure out what is the equation for the decrease. So that's going to be y equals, we're starting out, our initial population is 144 picas. It is decreasing by 8% each year, so that's 1 minus 0.08 to the x power. So if you simplified that, that's 144 times 0.92 to the x power. Okay, that's my equation. They want to know, how does the decrease in population for years 1 to 5 compare to the population for years 6 to 10? So what we're going to do is, I know I labeled this y, but I want to change this to f of x just so I can show you what I'm plugging in, okay? So f of x, I want to find f of 1. So that'll be 144 times 0.92 to the 1 power. That is equal to about, again, I'm rounding here, 132. Then I find to the 5. So f of 5 is 144 times 0.92 to the 5th power. That would be around 95. And basically, so we have 0.1132 and 595. And basically, you figure out the rate of change there. It says, how does the decrease in the population for years 1 to 5 compare to the population for years 6 to 10? So they're looking for the rate of change. How fast is it decreasing the first 4 years? So we're going to say 95 minus 132 over 5 minus 1. And so when you do that, you'll get negative 37 over 4, which is negative 9.25. Okay, so that's decreasing at a rate of 9.25 picas per 4 years. Okay, per year, excuse me, not per 4 years, per year. 37 picas per 4 years, but about negative 9.25 per year. So we do the same thing for year 6 to 10. So we're going to find f of 6 and f of 10. So 144 times 0.92 to the 6th power, and 144 times 0.92 to the 10th power. So if we go to the 6th power, we'll realize that that is about 87. Again, that's an estimate. That's not exact. We're rounding there. And 10, if you plug it in, you get about 63. And so we have 6 and 87 and 10 and 63. And we do the same thing. We find their slopes. So 63 minus 87 divided by 10 minus 6. That is negative, let's see here, is that 24? Negative 24. And negative 24 divided by 4 is negative 6. So, as you can see, between years 1 and 2, the population is decreasing faster than it is between years 6 to 10. So, 1 to 5, it's decreasing negative 9.25 picas per year. 6 to 10 years, it's decreasing 6 picas per year. Okay? So when it says to compare, you're just going to say it's decreasing faster from 1 to 5 than it is 6 to 10. Okay? It just decreases faster from 1 to 5. So here we go. Again, same thing. How would the average rate of change over years 1 to 5 and years 6 to 10 be affected if the population increased at a rate of 8%? So this time, we're increasing it. So that changes my equation. We're going to have f of x equals, we're still starting out with 144 picas, but this time we're going to increase it. So we're going to add 0.08 to our 1. Okay? Well, that's f of x equals 144 times 1.08 to the x power. And let's see here. So we start all this again. So f of 1 would be 144 times 1.08 to the 1 power. If you put that in your calculator, you will see, let's see here, 144 times 1.08, that is 155.52. If you do f of 5, that is 211.58. That's rounded. And if you subtract those, so you'll have 211.58 minus 155.52 divided by 5 minus 1. So 211.58 minus 155.52 is equal to 56.06 divided by 4. That's 14.01. So really 14 picas, we'll just say average. We'll round to 14 picas increase per year for the per year for the years 1 to 5. We do the same thing for years 6 to 10. So 144 times 1.08 to the 6th. And f of 10 equals 144 times 1.08 to the 10th power. And we plug those in. Let me plug them in real quick. Sorry about that. Takes a little time. So that would be 6. That's going to be 228.51. If you do 10, that'll be 310.89. And we do the same thing. So 310.89 minus 228.51 divided by 10 minus 6. So I know 4 is on the bottom. 228.51. That's 82.38 on top. Divide that by 4, and we get about 20.6 6 picas per year growing from year 6 to 10. So it actually grows faster from 6 to 10, but it decreases faster from 1 to 5. Okay? All right, last type of problem here. Sometimes they have really big values. And so what is this? This one, it says Rich is comparing the cost of maintaining a car, okay, cost of maintaining, with the depreciating value of the car. So we're comparing how much does it cost to maintain the car with the value of the car. When will the cost and the value be the same? So in other words, the same means when are they going to be equal? So it tells you the value here says it starts at 20,000. So we'll say f of x equals 20,000 times, it's decreasing at 15%, so 1 minus 0.15 to the x power. So simplified, that'll be 20,000 times 0.85 to the x power. G of x, I'm just calling it something different. This is the maintenance cost, so it's $500 for the first year, and it's increasing, so 1 plus 0.28 to the x power. So 500 times 1.28 to the x power. And basically we just need to set those equal to each other. Now, really the only way we know how to do this right now is to graph them and to compare the graphs. So let me go to my graphs. Now before I do that, 20,000 and 500, that's very big. So that's going to be hard to fit on our graphs. So we can change that. We can, instead of letting it be 20,000, we can just say, hey, we're going to count this first number as, we're going to count it in thousands. So how many thousands is 20,000? 20. Okay, and the only reason I'm doing that is so my graph will fit on my calculator. Okay, so how many thousands is 500? 500 is 0.5 thousands. So I know that might be a little confusing, but understand, we're just doing that so it will fit on our computer screen, because 20,000 and 500 are not going to probably fit on our on our calculator screen. So if you change them to 20 and 0.5, and here, let me pull up a calculator here. So we're going to have y equals, let me clear out what I had here. We had 20 times 0.85 to the x power. And the other one was 0.5 times 1.28 to the x power. And we graph them. We'll see that their intersection over here is where the blue line crosses the black line. So you can get their intersection point because we're trying to figure out where are they equal. So I'm going to go to second and trace. And you'll scroll down, you'll see number 5 says intersect. So if I hit number 5, and I move my cursor, okay, and you want to move your cursor as close as you can to that intersection, and basically you just want to put it a little bit on the left side of it, enter, and then go to the right and hit enter, and the calculator will tell you my intersection is 9 and 4.6, we'll just say, we'll round, okay? So what does that mean for my answer? Well, that means how many years will it take? 9 years. And how much will it cost? 4.6. Well, remember, that's in thousands. So that's 4,600, basically. Okay? So after 9 years, it'll cost $4,600 to take care of, as well as that's how much it will be valued at. It'll cost you, if you wanted to sell it, you could sell it for $4,600. Okay, so 9 years, it would be about the same. When will the cost and value be about the same? So the cost and value will be both about $4,600 in 9 years. Okay. Sometimes this problem says explain how to use tables on a graphing calculator to answer this question. So we just used the graph. We found the intersection of them. I could also use the table. So I've already got them in here. So if I hit second and graph and go to my table, we're basically just looking for where the y's are equal. So if you scroll down to number 9, you'll see that y1 is 5.6 and y2 is also 4.6, and y2 is also 4.6. So we get the same answer looking at the table. So you can look at your table, you can look at your graph. It does not matter. So that is our lesson for the day. Just a quick summary of what we've learned. We've got exponential growth, exponential decay, and we also talked about compound interest, which again, compound interest is also exponential growth. It's just a little bit different equation. Growth, basically you're adding your growth rate, or you are subtracting your decay rate, and basically it's just knowing the formulas and plugging in. I hope this video helps. Y'all have a good day, and as always, stay above the line.